he's now at the Institute, and where he's doing research on the relationship between field theories and string theories, focusing especially on the nature of supersymmetry breaking. With you, Simeon Hellerman.
I'd like to start off by saying that I am honored beyond words to be invited to address this gathering on the centenary of Albert Einstein's miraculous year at the illustrious institution which he later made his home. Now, Philip Argyris mentioned specifically Einstein's use of logic, and I think that's a very good thing to point out, because although fairly or unfairly, Einstein never considered himself to be a great practitioner of mathematics as applied to the physical sciences. He was absolutely unparalleled in his use of elementary logic to reach extremely startling but true conclusions about the physical world. Now, the story I'm going to tell you today will really illustrate that, the story of Einstein's theory of Brownian motion and its connection with the atomic theory. But our story, which will involve what phenomenon Einstein explained, how he explained it, and why it was important. Okay, our story will begin not with a physicist, but with a botanist by the name of Robert Brown, a Scottish botanist and at the time curator of the British Museum, who observed that pollen grains suspended in water, instead of remaining stationary or falling to the bottom of the suspension, would move around randomly, apparently at random, in jagged, zigzagging motions, tracing out a path which didn't seem to have any real pattern to it. So this process, which could be easily seen with a microscope, gained the name of Brownian motion. And as the years went by, well, it was studied by various experimenters, and a lot of curious things were seen. One of them was that this was not a transient effect. Brownian motion was not a transient effect. If you took some pollen and sealed it up in a sealed glass container of water and left it for a long time, it didn't matter how long you left it, the zigzagging wouldn't stop. Okay, it just kept on zigzagging. And in fact, an experiment was done where the pollen was observed for a full year, and the motion just continued completely undiminished. So that was sort of mysterious in its own way. Some patterns were discerned. One of them was that the effect depended very much on viscosity. So, for instance, a very viscous fluid like if you put pollen into a very viscous fluid like glycerol, you would see much smaller and slower wandering than in a much less viscous fluid like alcohol. Okay. And but maybe most importantly, certainly the thing which caught Einstein's attention was that the motion depended very strongly on the temperature. Okay, so heating up the water would greatly increase the speed of zigzagging, of random zigzagging of the pollen motes. Okay, and there was also a dependence on the size of the pollen motes, not the weight of them, but just of the radial size, the typical size of the little pollen particles. Okay. So Einstein said, well, let's see. instead of looking for some deterministic way, some deterministic law for this motion, let's just assume it's random for all practical purposes, and it's affected by temperature. So randomness and temperature means that we should look at the statistical theory of heat, which was being developed in the later part of the 19th century. For about 50 years, this had been a subject of very intense research. Okay. So in order to explain Einstein's theory of Brownian motion, I'll have to give you some background about the developing theory of statistical mechanics. And I want to emphasize that this is really the story of physicists not taking their ideas seriously enough until Einstein, okay, who took the theory of statistical mechanics much more seriously than any of the people who had spent half a century developing it. So what is statistical mechanics? It's a branch of physics which aims to explain the macroscopic properties of ordinary matter in terms of the average behavior of microscopic, invisibly small constituents behaving under the influence of mechanical forces. Okay. So where did this idea come from? Why was it developed in the first place? So it really had to do with the puzzle of energy conservation in processes which involved heat. Okay. So heat is energy, and that was understood fairly early on. So the way you can see this is by noting that in processes like the ones which Newton studied to develop his mechanical laws, the energy of a ball rolling down a ramp is conserved if you count its energy properly. A potential piece, which depends on the position, a kinetic piece, which depends on the speed at which the ball is rolling, and that energy, which we'll call mechanical energy, both of those forms of mechanical energy, the sum total of those two is conserved in processes like the one Newton studied. But there's a much more common and familiar set of processes where mechanical energy is not conserved. And the illustrative example comes from not rolling but sliding a block down a ramp. And there's friction, and you start it off at rest, you give it a little push, and it can slide down the ramp and then come to rest. Okay. So it looks like energy isn't conserved. Certainly mechanical energy is not conserved in this process. But it was realized by several people that if you counted the heat that was generated, so if you see, I drew this diagram with little red lines coming off of the box, which means that the box heated up as a result of this friction against the ramp. So several people realized about the mid-19th century that if you take heat into account properly, then there is still a notion of conserved energy. You just have to include a heat piece. So it's a sort of they saw it as a sort of a formal mathematical statement, just that you could mathematically define a function u which just depended on, in a closed system, just depended on things like the temperature and the potential and mechanical energy, the mechanical energy of the system as well, and that a change in the in one sector, like the heat sector, would always be compensated by a change in the mechanical sector. Okay, so it just means that mechanical energy plus thermal energy in a closed system is constant over time, and this is called the first law of thermodynamics. Okay. And then there was an elaboration of this idea, which was extremely successful in explaining and describing the behavior of gases under various pressures and and temperatures. And the idea was that matter, in particular gases, are made up of microscopic molecular constituents, and these constituents are constantly in motion. They're constantly agitating. Even when you feel like the air is not moving, like there's no wind, on microscopic scales, the little constituents, the air molecules, are moving actually very quickly at hundreds of meters per second. Okay, so the most important thing is that all of the thermal energy in the gas is accounted for by this mechanical energy of the constituents, of the molecules. So the idea was that for these, at least for these gas systems, you could never have to worry about thermal energy as a separate thing. You could say there's no thermal energy in this gas, in this so-called ideal gas system. There's only mechanical energy of the constituents, and it's absolutely conserved. Okay, so that was their explanation for ideal gases of where this mysterious thermal conservation law came from. Okay, so what is an ideal gas? Well, an ideal gas is a model of a gas where the energy of the constituents is purely kinetic. So there aren't any long-range forces between them. So they just propagate in a straight line at constant speed until they collide, and then they bounce off each other at some other direction and speed. And one of the developers of this theory, Ludwig Boltzmann, proved that in the limit where you had a very large number of these billiard balls bouncing against each other, that eventually they would reach a statistical distribution which described a gas at rest or just moving with some constant speed, and all the thermal energy in the gas would be stored as the kinetic energy of these little billiards. Okay. And some beautiful laws were derived, such as the ideal gas law, which is that the pressure times the volume is equal to the temperature times a universal constant times a ratio, a certain ratio of the number of molecules in the gas to some fiduciary number of molecules, the number of molecules in a gram of hydrogen, which is called Avogadro's number, but that number wasn't really known. So all people could talk about in this ideal gas theory, and this was really its biggest weakness, all people could really talk about was ratios of numbers. So they didn't know how to take a box of gas and look at its temperature and its pressure and its volume and say, there are so many, such and such number of air molecules in this box. They could only talk about ratios of numbers of molecules. And this really made the atomic theory seem like, well, it's a successful mathematical model, but it's not very real. It's like, well, there are a lot of things that people say that about today. I mean, people sometimes like to draw a distinction between real physical objects and things which aren't quite real. You just think of them as sort of bookkeeping devices for real physical quantities. Because if you could just arbitrarily rescale the numbers of molecules in all gases simultaneously and get the same answers, it didn't really sound like these little constituents were very real, indivisible things. Okay. But Einstein was to prove this point of view wrong. And to show how we did this, let me just quickly describe two last ideas from statistical mechanics. So one of them is the idea of thermal equilibrium, which just says that two bodies in contact eventually come to the same temperature after enough time. And the second and most important for our purposes is the principle of equipartition, which says that if you have something which isn't just a billiard ball, but it has internal degrees of freedom, which can move around and vibrate, then those internal degrees of freedom get the same energy as the overall translational kinetic energy of the billiard ball. So with these two ideas, Einstein was able to explain Brownian motion and do a lot more too. Okay. So he said Brownian motion comes from the collision of macroscopic particles, such as a speck of pollen, with microscopic ones, such as a water molecule. Now, this sounds reasonable, but you have no idea what a radical sounding suggestion it was. Because, first of all, as it turned out, the order of magnitude of masses of these things were completely different. The order of magnitude was about 10 to the 20 different between the mass of a speck of pollen and the mass of a water molecule. But it was more than that. I mean, you can't compare two things. It's like an idea hitting a thing. A molecule is an idea. It's not a thing. So it can't hit a thing and make the thing move under a microscope. So this was why it sounded extremely, extremely strange. But in fact, Einstein was able to make some extremely sharp predictions out of this theory. So he asked himself, what happens if you treat a large, complicated object like a grain of pollen, just as if they were big, very big molecules with a lot of internal degrees of freedom and an enormous mass? What would happen then? Well, he said, he reasoned, the equipartition theorem would say that you don't have to worry about the internal degrees of freedom. You know that just the overall translational kinetic energy of the pollen speck has to be the same as any one of those water molecules once the pollen and the water come into thermal equilibrium. And since people knew that this effect lasted for a year or more, clearly the pollen and the water were in thermal equilibrium while Brownian motion was taking place. And this was really the only conceptual input he needed. So now we're going to solve a differential equation. So I'll just call on people in the audience. So he wrote down a differential equation for essentially for the average deviation of the water molecule from the origin after some period of time. So, excuse me, for the pollen speck from the origin after some period of time. So it would start out at x equals 0 at some time, and then it would wander randomly. And okay, so what he did was he wrote a differential equation with two terms. So we're going to call them the microscopic term and the macroscopic term. So the point is that the first term, the microscopic term, is just equal to x dot squared. So the square of the time derivative of the position of the pollen speck, but that's just proportional to the kinetic energy of the pollen speck, and that's exactly given by the equipartition principle. Okay, so it's predicted by microscopic statistical mechanics to be some fixed number in terms of the mass, and importantly, in terms of Avogadro's number. The second quantity, the macroscopic term, is just the viscous drag on the pollen speck. So this is a term, a force you get just by considering the pollen speck to be a big sphere in the water. So there's some drag on it. So in one term, you treat the speck like a little big complicated molecule. In the other term, you treat it like a big classical sphere, and you add them. So this is the genius of Einstein, that he realized that you could just do this, even if it sounds weird. So, and importantly, the viscous drag on a sphere depends on the dynamical viscosity coefficient. So I assume you've all found the solution by now. And remember that these quantities are really statistical averages of motions of the Pollen speck. Okay. But in long times compared to the typical time for collisions of the speck with water molecules, the solution simplifies very greatly, and you find that the typical statistical average of the distance traveled by the pollen speck is proportional to the square root of the time, exactly in accordance with observations, proportional to the square root of the temperature. So as we saw, it does go up with temperature. Inversely proportional to the square root of the size of the speck, in accordance with observation, and most interestingly, inversely proportional to the square root of Avogadro's number. So all these other quantities were known, were things that you could get from other sources or just measure directly. But what this did was it gave you an experimental way of measuring the number of molecules in a gram of hydrogen. So this is really astonishing, because with this paper, molecules turned from ideas, from little bookkeeping devices, into things. I mean, it's as if one of those little boxes you use when you do calculus to break up the area under a curve. It's like one of those little boxes fell on your toe and broke it. Very, very strange. But it really connected the micro and macro worlds. So this is what we learn. First of all, it is not intellectually irresponsible to extrapolate over 20 orders of magnitude when the thing you're extrapolating is basic logic. Okay, so physical laws might apply to differently at different scales, but the laws of statistical mechanics are just based on logic. They're not based on anything else. And logic has to apply the same to big things as to little things. Okay. So Brownian motion gives us a great and direct way of seeing the microscopic world. And so I'll illustrate that with a picture and end up by saying happy anniversary, Albert.
Our next speaker will be Professor Steve Adler, a professor here at the Institute. Steve got his PhD from Princeton University and then held some positions at Harvard and Cornell, and then he came to the Institute many years ago. Steve has shown that abstract ideas about symmetries can be made to predict concrete measurements. They can be turned into concrete predictions. So he did this for symmetries of particle theories, and his approach to symmetries is one of the cornerstones for our understanding of modern particle physics. Steve has recently been thinking about generalized forms of quantum mechanics. So he, as well as Einstein, has thought a lot about the meaning of quantum mechanics, and Steve will tell us about Einstein and quantum mechanics.
Okay, my title is Einstein and Quantum Mechanics, a Love-Hate Relationship. I chose my title somewhat facetiously to emphasize the fact that Einstein made fundamental contributions to the inception of quantum theory, as well as becoming deeply critical of it. Perhaps a less pop title would be Einstein and Quantum Mechanics, Paternity and Alienation. Einstein was indeed one of the founding fathers of quantum mechanics. As you have heard from Graham Cribbs, his 1905 paper on the photoelectric effect established the fact that light cannot be viewed solely as a wave, as the optics of Young and the electrodynamics of Maxwell had it, but had corpuscular aspects as well, as Newton had earlier advocated. Light consists of streams of quanta, which we now call photons, each of which satisfies the energy-frequency relation E equals h times nu, or in shorthand, h nu. Where E is the energy of the photon, h is Planck's constant, and nu is its frequency, the number of vibrations per second. Einstein thought on and off about issues concerning radiation between 1905 and 1911, when he immersed himself for 4 years in the creation of general relativity. With general relativity completed in late 1915, he returned to work on light quanta and made a major advance in 1916, when he discovered the laws of interaction of light quanta with matter. Einstein was a great master at getting profound conclusions by insightful use of relatively simple thermodynamic arguments. And the 1916 paper was a prime example of this. The question Einstein asked was the following. Consider light quanta in a cavity at a temperature T with a spectrum given by Planck's famous formula, rho of nu T, that's the density of oscillations of frequency nu at temperature T, is some constants times the cube of the frequency divided by the exponential of h nu divided by the temperature minus 1. Then how do the rates of emission and absorption of light quanta from the atoms in the walls of the cavity arrange for this equilibrium to be maintained? He answered this as follows. From Bohr's model of the atom, it was already known that atoms can be in states of discrete energies. Consider a pair E1, E sub 1, and E sub 2 of such energies, with a difference E sub 2 minus E sub 1 equal to h nu, with nu the frequency of a photon, with an energy matching the energy difference between the two atomic levels. Then Einstein postulated the following. He said, the rate of emission of photons of frequency nu must be proportional to the number of atoms in the upper state times two terms here. A constant reflecting the spontaneous emission of photons, and a second term, a constant times the density of photons already present, reflecting an induced emission. Also, the rate of absorption of photons of frequency nu is the number of atoms in state 1 times the number of photons already present in the cavity times a constant reflecting the rate at which the atom can be pumped up from state 1 to state 2. The first line of the formula, the second line of the formula seems rather intuitive, that the rate of absorption should be proportional to both the product of the number of atoms in the lower state and the number of photons that are present to be absorbed. The second line was more audacious in postulating that there's a spontaneous emission and also an induced emission. That was really a bold stroke. I won't repeat Einstein's reasoning, which involves some simple algebra, together with the fact that statistical mechanics says the following. From just the laws of statistical mechanics, Einstein knew that the number of atoms in the lower energy state divided by the number of atoms in the upper energy state is the exponential of the difference in the energies divided by the temperature. Or if the difference in energies matches h nu, it's e to the h nu over t. This is just Maxwell-Boltzmann statistics. And the thing that you'll notice, and that Einstein undoubtedly noticed, is that this exponential is exactly the same as the one in Planck's formula. So if you now equate the rate of emission, the rate of absorption, and do some simple algebra, you find that the absorption coefficient B12, the spontaneous emission A21, and the induced emission coefficient or stimulated emission coefficient B21 all must be non-zero with a definite relationship between them that Einstein calculated. You need all three of those components in order to match the Planck radiation formula. About his derivation, Einstein wrote, quote, "The simplicity of the hypotheses makes it seem probable to me that these will become the basis of the future theoretical description." End quote. This indeed happened when the quantum theory of radiation was established by Dirac in 1927. It yielded precisely Einstein's relations between the A and B radiation coefficients. The stimulated emission process that Einstein first postulated is currently of great technological importance because it is the basis of the laser. In a laser, atoms in a cavity are pumped to an excited state E sub 2 above a lower state E sub 1. A few photons emitted by spontaneous emission trigger the emission of more photons by stimulated emission, which trigger further emissions, resulting in an intense coherent photon beam. Einstein went on in another 1916 paper to show, again by thermodynamic arguments, that the photon carries not only energy but also momentum. Just to recall, for a massive object, momentum is the product of mass times velocity. This formula has to be modified when velocities approach that of light, but the concept of momentum remains valid. Thinking about the implications of photon momentum on the one hand and spontaneous emission on the other was the beginning of Einstein's doubts about quantum mechanics. If an atom or molecule spontaneously emits a photon and the photon carries momentum, then conservation of momentum requires that the atom must recoil, just as a rifle recoils when a bullet is fired. But since the direction of photon emission is random, the direction of recoil of the atom is random. It cannot be predicted. Additionally, the time of spontaneous emission is also random. Einstein's equilibrium calculation postulates a rate of spontaneous emission, but does not say when a given atom will emit. This also cannot be predicted. Einstein found the role of chance here deeply disturbing and wrote that it is, quote, a weakness of the theory that it leaves time and direction of elementary processes to chance, end quote. Thus, Einstein's disenchantment with quantum mechanics began with his work on radiation during the period 1916 to 1917. Let me now jump to 1926. Schrödinger had discovered his wave equation, which correctly predicted the excitation energies E sub 1, E sub 2 of atoms as being like the modes of vibration of a piano string or a bell. His equation involved a wave function, psi, that depends on spatial position, the interpretation of which remained obscure. In 1926, Max Born published a fundamental paper in which he proposed the correct interpretation of the wave function. Let psi be the wave function for an electron at a point in an atom. So we'll say this is a point inside an atom. Then Born's rule states that the absolute value squared of the wave function gives the probability of finding the electron in a small unit volume around that point. So some explication here. The absolute value squared has to be used because the wave function is not a real number, but a complex number. Writing psi equals p plus iq, where p and q are the real and imaginary parts, the absolute value squared is just absolute value psi squared is p times p plus q times q. Or in other words, p squared plus q squared. This is the Born rule. And if you think of p and q as being the legs of a right triangle, then the square of the length of the hypotenuse gives Born's probability. So here again, the probabilistic nature of quantum theory is evident. Just as we cannot say in which direction an atom that emits a photon recoils and when it will recoil, but can only give probabilities, so we cannot say where in an atom an electron will be found, but only give probabilities, that it can be probabilities, and these probabilities can be computed from the wave function. Needless to say, Einstein was profoundly uneasy about this, and in a famous letter to Max Born wrote, quote, quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice, end quote. Einstein's disenchantment with quantum theory led him to stand aloof from the great successes of quantum theory and its relativistic version, quantum field theory, between 1925 and his death in 1955. Freeman Dyson, who was at the Institute during the period when Einstein was still alive, remarked to me that he never talked to Einstein, who was simply not interested in what the young people whom Robert Oppenheimer had assembled here were doing. Nonetheless, during the pre-World War II period, when Einstein was already at the Institute, Einstein, Podolsky, and Rosen, called EPR for short, wrote a classic paper that has greatly influenced subsequent discussion of quantum theory. The title of the paper is, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And that's the first page of the paper. The paper considers a situation in which two systems, 1 and 2, interact briefly and then move far apart, and discusses how measurements of physical quantities of the second system can give information about the first, even though there is no direct contact between them once they have separated, and even though the choice of quantities to be measured on the second system can be made after the systems are separated. The EPR paper is a rather unusual beast. Its conclusion that, quote, "no reasonable definition of reality could be expected to permit this," end quote, the "this" referring to things that are predicted by quantum theory and known to agree with experiment, is now regarded as being based on an overly restrictive definition by EPR of what they term, quote, "elements of physical reality." So to talk about an EPR paradox is inaccurate. However, when the basic EPR setup is rephrased not in terms of position and momentum variables, as in their paper, but in terms of electron or photon spin variables, it has profound implications for both quantum technology and for fundamental theory. For this reason, the EPR paper is still a highly cited and highly accessed paper. Physical Review maintains an archive, PROLA, Physical Review Online Archive. And Martin Bloom, the American Physical Society editor-in-chief, told me that the EPR paper was the most downloaded paper from PROLA in 2003, and one of the most highly cited of the older classic papers published in the Physical Review. To illustrate why there is so much current interest in the EPR paper, let me give two examples, one drawn from technology, one from fundamental physics. Both are based on an EPR setup using entangled spins of particles, which can be experimentally realized using either photons or electrons. I will use the language of electron spins, even though for photons these are realized experimentally through use of different polarizations. Consider an apparatus that emits two particles correlated in a spin zero state, one moving to the left and one to the right. Someone on the far right, measuring spin along any axis, let's say north-south, will find a 50% chance of spin up along his chosen axis and a 50% chance of spin down. But once he has made this measurement, he can predict with certainty what the spin measured along the same axis to the far left will be. To give total spin zero, it must be the opposite of what he has measured. The initial coherent superposition of up right and down left plus down right and up left has been reduced by the measurement process on the right to a single term. If the observer on the right finds up, the observer on the left must find down, and if the observer on the right finds down, the one on the left must find up. This is the kind of non-local correlation that EPR found unpalatable. Given that quantum mechanics generates these strange entanglements, let us put them to practical use. Here is how the EPR setup can be used for transmitting a secure code, as was first proposed by Charles Bennett of IBM and Gilles Bressard of the University of Montreal. What I'll describe is a slight variant of their original proposal due to Arthur Eckert of Oxford, which uses EPR. Consider two observers, Alice and Bob. In between, or for that matter in Alice's laboratory, there is an emitter of EPR entangled photon pairs. One member, so we have a source here, one member of the pair going to Alice and one member going to Bob. Alice and Bob each also have a penny to flip and an unsecure telephone line to compare the results of their flips. They each flip their penny and then measure an EPR pair, choosing as the measurement axis north-south if their penny comes up heads, and east-west if their penny comes up tails. They record their measurement results and then on the unsecured telephone line compare the results of their coin flips, but not the measurement results. If they have both flipped heads or both tails, they keep the measurement result. If one is flipped heads and the other tails, they ignore the measurement result. They then convert the measurement result to a code as follows. Alice assigns a 1 if her photon spin pointed north or west, 0 if her photon spin pointed south or east. So Alice assigns 1 if it's north or west, and 0 if it's south or east. Since quantum mechanics has correlated Bob's photon to point oppositely to Alice's when they measure on the same axes, he knows that when his photon spin pointed south or east, he should assign a 1 to match Alice. And when his photon spin pointed north or west, he should assign 0 to match Alice. In other words, Bob, in this correlated pair along a north-south axis, Bob's photon is down when Alice's is up, or Bob's photon is south, I should say, when Alice's is north, and Bob's is north when Alice's is south. If they use an east-west axis, same formula because the state is rotationally invariant, Bob's points west when Alice's points east, and Bob's points east when Alice's points west. They can then use a string of 1s and 0s as a one-time pad to encrypt a message. Note that neither one creates the code by themselves. It is the conjunction of both of their random coin flips that produces the choice of axes. Now consider the security of the code. An eavesdropper, Eve, tapping the phone line, will know the sequence of axes used in the measurement, but she will not know the measurement results, which determine whether that digit of the code contains a 1 or a 0. Because the existence of non-local quantum entanglement has allowed Alice and Bob to know what each other has found without communicating it on the telephone line. The only way for Eve to know is to intercept and measure the photon, which reveals her presence to Alice and Bob by destroying the quantum coherence that creates their code. They would find gibberish when they attempted to decode the message and conclude that someone has observed one of their photons. That there is no other way for Eve to operate is a consequence of a quantum mechanical theorem called the no-cloning theorem, which states that it is not possible to build a machine to absorb a quantum state and re-emit that quantum state unchanged together with a perfect copy. If Eve could clone the photon going to Bob, she could resend the original photon to Bob and keep a perfect copy, which she could then measure and thus break the code, while not destroying the code. But this is not possible. The proof of the no-cloning theorem is basically a transcription into quantum language of the following simple observation. Cloning a state is like squaring a number. Suppose we have a machine that produces the square of any number. So machine acting on A produces A times A for all numbers A. Then the machine cannot be a linear machine. In other words, this is incompatible with M acting on A plus B is M acting on A plus M acting on B. Proof, A plus B times A plus B, just expanding, is A times A plus B times B. This part looks linear, but there's a cross term, twice A times B, something is left over. We can easily build a nonlinear computer to square numbers, but quantum dynamics without a measurement intervening is linear, and so cannot do cloning, the quantum analog of squaring a number. The kind of cryptography just described has been translated into hardware. On the web, you can find an article entitled Current Status of the DARPA Quantum Network, DARPA meaning Defense Advanced Research Projects Agency. which contains a picture of hardware operating on telecommunications fiber running between BBN Technologies in Cambridge, Boston University, and Harvard. And since the equipment has a different experiment on the preceding page with pairs of apparatus named Alice, Boris, Anna, and Bob, this is now here Alex and Barb. So here we have a rack, that's Alex, that's Barb. These are the two measuring systems. This is the source at BU that produces the entangled photon pairs that are then transmitted to Alex and Barb, who then flip coins and determine the axes of measurement. I'll leave it on for a minute. Now let me show how the EPR setup was used by theorist John Bell, with later experimental confirmation by Alain Aspect, to reach profound conclusions about the structure of quantum mechanics. So I'll talk now about the Bell inequalities briefly. Let Alice's choice of axis be called S sub A, and her measurement result M sub A. Similarly, let Bob's axis choice be called S sub B, and the measurement result M sub B. Let us suppose that there are hidden variables, H sub 1, H sub 2, and so forth, whose values, if known, would determine the measurement outcomes of both Alice and Bob. And further, let us suppose that these hidden variables act only locally. That is, given the values of these hidden variables, there is some function P of SA MA that depends on Alice's axes and measurement result and on the hidden variables that determines Alice's outcome, but it doesn't depend on any of Bob's values, either his axes or his measurements. And assuming that Bob's apparatus is identical, the same function P of SB MB and of the hidden variables determines what Bob sees. The hidden variables will have some probability distribution for them to occur, P, that depends just on the hidden variable values. Then the laws of probability say that the joint outcome probability, P of SA, MA, SB, MB, this is the probability for Alice to measure MA given axis choice SA, and Bob to measure MB given axis choice SB, is a sum over all of the hidden variable values times the probability for the hidden variables times the function that governs Alice's outcome times the function that governs Bob's outcome. Now, what John Bell proved is that given a hidden variable system of this type, the joint probability must obey certain inequalities called Bell inequalities, which are violated by the quantum mechanical formula for the joint probabilities. This violation has been confirmed by experiment. Hence, quantum mechanics cannot be described by deterministic local hidden variables. Thus, if Einstein is right and quantum theory is not the ultimate layer of physics, the layer underneath must be even weirder and involve non-locality of some sort. A garden variety classical dynamics is excluded by the Bell inequalities. Among the founding fathers of quantum mechanics, Bohr, Born, and Heisenberg were adamant in maintaining that quantum theory is the ultimate reality. Einstein, as we have seen, was a skeptic, and so also was Schrödinger. Peiss, in his book on Einstein, notes that, quote, more than once, Bohr mentioned to me that Schrödinger told him he might not have published his papers had he been able to foresee the consequences they would unleash, end quote. So let me now turn to Schrödinger's famous cat. The cat thought experiment goes back to Einstein's original malaise with quantum mechanics, the probabilistic aspect of spontaneous emission or of an analogous process, radioactive decay. Consider a chamber containing an atom or nucleus in an excited state. So I've drawn now the electron is in the upper energy level E sub 2, and there's a lower level E sub 1. There's a photon counter, a cat, and a mechanical linkage that breaks a flask of cyanide if the counter detects a photon emitted by the excited atom or nucleus decaying to the lower state, E sub 1. After waiting a while, the experimenter opens a container. He will, of course, find a live cat or a dead cat. But quantum theory, as applied to the whole setup, says that at the instant before he opened the container, the wave function was a superposition of one containing a live cat and the atom in the upper state E2, and one containing a dead cat and the atom in the lower state E sub 1. With a digital recorder substituted for the cyanide plus cat, this experiment is repeated thousands of times daily in laboratories all over the world. We never see macroscopic superpositions of measurement outcomes. Measurement always forces a choice between alternatives. This choice is described in orthodox quantum theory by an additional postulate, which states that measurement apparatuses are always classical objects not described by quantum theory, that give definite outcomes with probabilities described by the Born rule. But if we believe that quantum theory describes the whole universe, then why shouldn't we apply it to a mere laboratory-sized measurement apparatus? This is the so-called quantum measurement problem and continues to be a conundrum today, 80 years after the invention of the new quantum theory in the mid-1920s. There are two schools of thought for dealing with it and one school of non-thought. The school of non-thought is what we were all taught in quantum mechanics class. It works, so shut up and calculate. The attitude of most working physicists can be expressed in the words of Feynman, quote, "I cannot define the real problem, therefore I suspect there's no real problem, but I'm not sure there's no real problem," end quote. The two schools of thought form a dichotomy. Either one, quantum mechanics is an exactly correct theory, and we only have to improve on the orthodox interpretation without experimental consequences, or two, quantum mechanics is only a very accurate approximation to a more exact underlying theory that will encompass both quantum entanglement and quantum measurement in a unified way, and will make statements about where experimental deviations from the predictions of quantum theory might be expected. The first approach accepts the anti-Einsteinian view of Bohr, Born, and Heisenberg. The second approach accepts the skepticism voiced by Einstein and Schrödinger. Determining which of these two views is correct is an outstanding issue on the agenda of 21st century physics. The issue is relevant theoretically because current theoretical speculation is probing frontier areas, such as quantum gravity, where our laboratory-based intuitions may break down. Moreover, there are well-defined theoretical proposals for modifying quantum theory, such as phenomenological models for state vector reduction associated with Girardi, Ramini, and Weber, and with Pearl, and my own proposal of a new dynamics called trace dynamics as a fundamental theory underpinning quantum mechanics, on which I have written a book published last year. The issue is relevant experimentally because new precision techniques are generating the capability to look for quantum coherences and their breakdown in progressively larger systems. Sooner or later, proposals for modifications of quantum mechanics will be decisively restricted, or deviations from the standard theory will be found. Either way, doors on possible avenues for exploration will be opened and closed. Thank you.